Well, good day, everyone, and thank you for joining us today. My name is Dave Mercer, and I will be the moderator for our presentation. I'm a member of Fluor's Office of Technology, which focuses on using science and innovative engineering technology to build a better world. Our engineers, designers, and experts, that is, our people, are at the core of our success. Today's webinar is titled Noise Control in Design. Managing industrial noise is no longer just a regulatory requirement. It's a critical design factor influencing worker health, equipment selection, project risk, and overall facility performance. As global expectations for occupational hygiene, environmental compliance, and community impact continue to rise, noise control engineering has become an essential element of responsible project execution. Join Fluor SME Wayne Seeto for a focused session on using predictive modeling, acoustic simulations, and targeted mitigation to reduce project noise risks and avoid over-engineering of noise controls. Discover the surprising reasons why hearing protection isn't always effective, and how early design decisions can eliminate or significantly reduce noise risks at source. The presentation will feature animations and audio simulations designed to give participants an intuitive understanding of key concepts, including worker noise exposure, hearing loss, tinnitus, and sound propagation through the environment. This is perfect for facility operators, engineers, project managers, and HSE teams looking to engineer and deliver safer, quieter facilities. Now, to set the stage for today's webinar with a brief safety topic is Domian Verweemera. Domian, now over to you.
Thank you, Dave. During my work as a noise control engineer, it has always been very clear to me that exposure to high noise levels can lead to permanent and irreparable hearing loss, and that the prevention of hearing loss did lead to the occupational noise limits that I adhere to normally. But for this safety topic, Wayne suggested that I speak about the surprising effect that exposure to high noise levels also can have. A study performed in Sweden studied the effects on children of mothers who had been exposed to high noise levels during pregnancy. It studied the effect of children whose mother had a daily noise exposure of less than 75 dBA, with children whose mothers had exposure of more than 85 dBA. And the study found that there was a 27% to 82% increase of the risk of hearing damage to the baby. Daily noise exposure is the average noise level received during an 8-hour working day, to be clarified in this way. So the 82% increase of risk represented mothers working full-time with minimum leave and for the entire duration of the pregnancy. And the outcome of this study seems to show a dose relationship. The more time the developing baby is exposed to high noise, the higher the risk of hearing dysfunction. Other studies found that exposure to high noise levels during pregnancy is associated with maternal stress, fetal stress, preterm birth, low birth weight, impaired mental and health outcomes later in life, and also with impaired motor and cognitive functions in life for the child. It's obvious from this example that having the mom wearing hearing protection does not protect the developing baby. Some possible actions to consider are: survey the workplace to clearly show which areas have a noise level of more than 75 dBA. implement a noise conservation program for the workforce, and as part of that program, identify which roles are expected to work in high noise areas and conduct noise dosimetry to identify the daily noise exposure levels for the people in those roles. Consider a way to reduce the noise levels or reduce the time that people are exposed to the noise. And finally, provide education and training on the risks that high noise can cause to the workers and any developing babies. I will now hand over to Wayne, who will present the main topic. Over to you, Wayne.
Thanks, Domine. Hi, everyone. Our agenda for today is structured to build your understanding from fundamentals through to practical engineering applications. Your ears. We'll begin by exploring just how sensitive the human ear is and why that matters for noise exposure. Next, we'll take a clear look at how noise causes hearing damage, what tinnitus actually is, and what it might sound like to a sufferer, and the broader health, cognitive, and social impacts associated with high noise. Noise modelling. We'll walk through some basic acoustic concepts, how noise propagates through the environment, and how we use 3D modelling tools like SoundPlan to predict real-world noise levels. Noise control principles. From there, we'll explore using examples the engineering hierarchy of noise control, elimination, substitution, reducing the noise at source, and finally, path treatments such as enclosures and silencers. Targeted engineering solutions. Finally, we'll bring it all together to show how early design decisions and targeted engineering solutions can dramatically reduce project risk, improve compliance, and build quieter, safer, and more sustainable facilities. By the end of this session, you'll have a practical, engineering-focused framework for identifying the noise risks early and mitigating them effectively, long before they become costly challenges in construction or operations. I'm going to begin with a question for you to consider. Do you know how sensitive your ears are? Your inner ear, the cochlea, has tiny hair cells that move when sounds travel into your ears. That movement sends electrical signals to your brain, which is registered as sound. The hair cells in your inner ear can detect displacements as small as 0.2 nanometers. This is roughly the diameter of a single hydrogen atom. Such exquisite sensitivity means your ears can detect extremely quiet sounds. But it also means that it can be easily damaged. Hearing damage can occur when the hair cells experience excessive forces, either from a very loud, sudden noise, such as a single shot from a howitzer artillery gun, or from hearing moderate noise levels for a large proportion of your awake time, such as operating a leaf blower 8 hours a day, 5 days a week, over 20 years, without the use of hearing protection. To put everyday sounds into context, this chart shows sound pressure levels from typical noise sources, starting from 0 dB going up to 140 dB. 0 dB represents the quietest sound a healthy human ear can detect. There are very few places on Earth that quiet. You would need to be inside an anechoic chamber, completely isolated from outside noise to hear something that soft. A person breathing very quietly is roughly in this range. A pin drop is about 10 dB, and a calm rural area at night is around 30 dB. As we move up the scale, everyday sounds get much louder. A commuter train typically reaches 80 dBA. At 85 dBA, noise becomes hazardous if you're exposed for long periods. Many common appliances like a blender or a leaf blower operate at around 85 to 90 dBA. At these levels, hearing protection is strongly recommended. And without it, you should limit how long you're exposed. As a rough rule of thumb, if you're standing in front of a person and you have to shout to be heard, then you're hearing roughly 85 dBA of noise. The safe exposure time for noise at 85 dBA is about 8 hours. At 100 dBA, the typical noise level of mobile equipment such as a digger or tractor, the safe exposure time drops to around 15 minutes. At 120 dBA, which you might encounter near a crusher or other heavy industrial equipment, the safe exposure time is only 9 seconds. At 130 dBA, the typical noise of a jackhammer, and especially at 140 dBA, the noise level of a rocket or artillery fire, there is no safe exposure time. Even a moment of unprotected exposure could cause instant and permanent hearing loss. What does hearing damage look like? The first image shows what healthy hair cells in the inner ear look like. The hair cells are intact and upright. The second set of images show the progression of damage to hair cells after suffering damage due to excessive noise. They're completely broken off or have been bent or are deformed. Hearing loss can have devastating consequences for the sufferer. What does hearing damage sound like? We're going to play an audio simulation of what music would sound like if you suffer progressive hearing loss. The music is filtered to simulate 40 years of progressive, noise-induced hearing loss in 5-year increments, with each 5-year increment indicated by a beep. Unfortunately, if you already suffer significant hearing loss, you may find it harder to notice the difference in clarity. Hearing damage can also cause other health impacts, such as tinnitus. Tinnitus is a medical condition where a person perceives a noise or a ringing sound in their ears without there being an external source of noise. The actual sound varies from person to person, but common descriptions include wailing, like a siren, whistling, hissing, buzzing, or roaring. The following is an audio simulation of what tinnitus might sound like for various sufferers. They might be uncomfortable for some people to listen to, especially if you already suffer from tinnitus. So please turn down the volume on your headset or mute the sound while the sounds are being played if it gets too uncomfortable. Some of these are very high frequency sounds, so for those who already suffer hearing loss, you might not even hear these sounds.
Noise can cause tinnitus too, a constant ringing or rumbling or buzzing in your ears that is there all the time, but is really noticeable when it's quiet or when you're trying to go to sleep.
Imagine hearing that while you're trying to get to sleep at night. Hearing damage doesn't just affect your ears, it affects your life. hearing loss and tinnitus have been linked to social isolation, cognitive decline, dementia risk, depression and anxiety, accelerated brain aging or atrophy, and increased suicide risk factors. Even when noise isn't loud enough to cause hearing damage, it can still impact your health in other ways. It can hamper your ability to concentrate, to communicate, and to rest. We can't expect members of the public to wear hearing protection in these circumstances, nor should we expect workers to wear hearing protection in the office when noise is affecting people's ability to concentrate and communicate. We should also be cautious about relying on hearing protection as the primary method of protecting the hearing of workers in high noise work environments. The bottom line is we cannot rely on hearing protection alone. Industry-wide, that approach has failed and is not a valid solution for many circumstances, as we have already seen. So if hearing protection is not the optimal solution, what is? Real prevention starts with engineering out the noise at source. This responsibility ultimately rests with the employer or facility operator, who must ensure that noise levels in the workplace and those emitted into the surrounding community are as low as reasonably achievable. As an engineering company, our role is to design facilities that are inherently quieter. We do this by identifying significant noise sources early in the design process and applying proven noise control engineering principles to minimize their impact. So how do we do this? We start by looking at the engineering design of the plant and identifying the significant noise sources. This can include equipment that moves gas, such as compressors, fans, gas steam turbines, and any vents to atmosphere. We also consider equipment that handles liquid, such as pumps, liquid turbines, or water sprays. There's equipment that vibrates due to the movement of solid materials, such as hoppers, chutes, shaker screens, or mills. There is also equipment that burns gases or liquids, such as flares, gas turbines, or internal combustion engines. You can see that all of these sources have something in common. They all involve high energy or high power. Let's stop and think about what's happening at a fundamental level with the generation of noise. Imagine you have a speaker connected to an amplifier, and that speaker is making noise inside a tube. The amplifier is providing electrical power to the speaker. The speaker converts that electrical power into mechanical power. Some of the mechanical power is transferred to the air molecules near the speaker, and the amount of power that is transferred to the air is called the sound power. The sound power propagates down the tube as a wave. The mechanical power that is not transferred to the air is lost as heat. Sound power level, shortened to LW or SWL or PWL, is the parameter that we work with in noise modeling. It is the parameter that characterizes the noise source. In other words, sound power level is independent of the receiver or the environment. But what we are more familiar with is what we perceive with our ears, or what we see on a sound level meter. This is the sound pressure level, shortened to either LP or SPL. The sound pressure on your ears is the result of the sound power. The sound pressure level characterizes the noise at the receiver, taking into account the environment and the distance between the source and receiver. To show how the sound pressure level changes for a fixed sound power level, let's consider a very simple case of a pump sitting in the open and a worker standing near the pump. The pump has, say, a sound power level of 100 dBA. If the worker is standing 1 meter from the pump, the sound pressure level is 85 dBA. If the worker walks away from the pump and is now 10 meters from the pump, the sound pressure level drops to 70 dBA. If there's a solid wall behind the worker, some of the noise will reflect off the wall back to the worker and could increase the sound pressure level at the worker by 3 dB to 73 dBA. If we now place a barrier in front of the worker, that could reduce the noise from the pump. The noise needs to travel over the edge of the barrier to reach the worker, and this has the effect of reducing the sound pressure level by, say, 5 dB to 68 dBA. This example serves to illustrate that the sound power level characterizes the source and does not change. The resulting sound pressure level at the receiver changes according to the distance from the source and the surrounding environment, which could increase or decrease the sound pressure level. So let's zoom out and look at how noise behaves as it propagates through the environment. There are two main environmental factors that influence the propagation of noise: wind and air temperature. We'll look at what conditions give rise to enhanced sound propagation. Firstly, we have wind blowing in the direction of the receiver and with a wind speed gradient. The length of the wind icons represents the velocity of the wind. The wind speed increases as you increase in height. Air temperature is a factor in sound propagation because it affects the speed of sound. In this example, temperature increases with increasing height. This condition normally occurs in the very early hours of the morning, just before sunrise. Under these conditions, the path of sound from the noise source curves in a downward direction towards the receiver. Noise levels at this receiver will be increased. Consider the converse situation. The wind is blowing away from the receiver, and the temperature gradient is reversed. The temperature decreases as you increase in height. The sound will tend to bend in the upward direction, away from the ground. Noise levels at the receiver will be attenuated. In this example, though, some of the noise will still hit the receiver, since the receiver is at an elevated height and water is a very effective reflector of noise. Once we have identified the significant sources of noise within a plant, we create a 3D noise model of the plant. There are a number of noise modeling packages available in the market, but the one that we use is SoundPlan. Generally, they all work in a similar way to each other. You start by importing drawings or images of the plant that you wish to model. Then you input data to model the ground, the noise sources, solid objects such as buildings or barriers, the environment, and the receivers. Then you define and execute the calculations for predicting the noise levels. And lastly, you present the results. All the significant noise sources are entered in the model as either point sources, line sources, aerial sources, or industrial buildings. Here's an example of a noise model showing the different ways that noise sources can be represented in the model. Point sources. These are sources that are physically small in size, such as small pumps or sirens. Line sources. These are sources that have one significant dimension, such as piping or conveyors. Area sources. These are sources that are significant in terms of area, such as the combustion air inlets of a gas turbine or air cooler fans. Industrial buildings. These are sources that are physically large and radiate noise from some or all of the facades, such as a waste heat recovery unit or an acoustic enclosure. We're going to take a closer look at industrial buildings on the next two slides. Here's an example of what an industrial building might look like. There are noise sources inside the building, such as a compressor, HVAC equipment and ducting. These radiate noise into the building interior. The noise bounces around, reflecting off the hard, acoustically reflective surfaces, such as the steel, cladding and concrete. Some of the noise is absorbed by acoustically absorbent material. Having acoustic absorption inside plant rooms is good engineering, as it will reduce the level of reverberant noise. A small amount of that noise is transmitted through the walls and roof, but most of the noise will eventually find their way out through the openings in the building, such as the building ventilation air inlets and outlets. Notice that one noise source inside the building, the extract fan, is piped directly out of the building. Noise radiates from the external piping and from the opening at the end of the pipe. This is a screenshot from some plan showing how the industrial building would be modelled. There are specific parts of the building that are defined as significant noise sources, such as the dark red rectangle labelled as an area source, representing the ventilation air outlet. The object labelled as a point source is the extract fan discharge that was piped directly out of the building, and the external piping of the extract fan is represented as a line source. Once all the inputs have been entered into the model and the calculations have been performed by the modelling program, what do we get from the results? Noise contours are one way to present the results of the noise calculations. We can produce noise contours at ground level or at any height above ground level. These noise contours show the expected noise levels from 55 dBA to 100 dBA in 5 dB bands. These contours enable you to quickly identify the areas within the plant that are particularly noisy, where you may need to focus your noise control efforts on. If you can't reduce the noise levels to below the safe limit, then these contours help to define the areas within which hearing protection must be worn. For assessing community noise impacts, instead of noise contours, we normally conduct detailed noise calculations at the specific receiver locations. In this example, we have an industrial plant affecting 3 community receptors. In this example, the noise limit is 49 dBA at each of the receptors. There is also a fence line receiver on the northern fence, but at this receptor, the noise limit is 67 dBA since it is not associated with the external community. Here are the results of the noise levels at each of the receivers. For 3 of the receivers, the noise levels are predicted to be below the noise limit, so we are expecting compliance. For the southern receiver, the predicted noise level exceeds the noise limit. We can dive deeper into the results to see what specific items of equipment are the dominant contributors to the exceedance. What we are looking at is a listing of equipment showing how much noise that piece of equipment is contributing to the overall noise level at the southern receiver, ranked by most significant to least significant. The noisiest equipment item is the urea bucket elevator, contributing 44.1 dBA out of the total 53.8 dBA. The red cells show the noise levels without any noise controls. The green cells show what the noise levels would be when the noise reductions are applied. We target the higher ranked noise sources for noise control, and we aim for a balanced result. This means that the noisiest items get the most noise reductions, and the less noisy items require less reductions. The level of reduction that's required then tells us what sort of noise control would be required, ranging from high-spec controls like acoustic enclosures and silencers to lower-spec controls like blankets or barriers. This ensures that you don't over-engineer the noise controls on any particular piece of equipment. Here is one iteration showing the target noise reductions that will achieve compliance compliance to the noise limit. You can see that we are looking for 11 dB reduction on the noisiest item, which could be achieved with an acoustic enclosure. And near the bottom, we see we need 5 dB reduction on the items that are less significant, which for fans could be achieved with a flow diffuser or a local noise barrier. Items that require less than 10 dB of reduction may not require acoustic enclosures and could probably be achieved with blankets or local noise barriers. Most of the time when people talk about noise controls, the conversation usually focuses on controls like acoustic enclosures and silencers. But there are better ways to reduce the noise, and this can be examined through the general principles of noise control. Elimination. Don't generate the noise in the first place if it can be helped. Eliminating the noise source altogether would be ideal if it can be done practically. An example of this would be to redesign your plant so that instead of relying on air coolers to provide the necessary cooling duty for your plant, to utilize cold water from, say, a ground source heat pump or a local body of cold water. This example could be useful when considering the cooling options for an LNG plant or a data center during the concept development phase of the project. Substitution. If you can't eliminate the equipment entirely, then choosing a quieter version is the next consideration. An example from the mining industry is the substitution of diesel-powered mobile equipment, such as haul trucks, with electrically powered mobile equipment. Replacing solids handling equipment that has large reciprocating forces with something that has slow rotating forces can potentially reduce noise. One example of this from the mining industry is replacing a reciprocating vibration shaker screen with a slowly rotating trommel screen. Both screens enable the sorting of rock and ore of varying sizes, but the shaker screens generate much higher noise levels due to the high impact forces of the rock and ore against the screen body. The trommel generates much less noise due to the low speed of the trommel and the much reduced impact forces from the rock and ore against the trommel screen. As with elimination, the principle of substituting with quiet equipment is most effective during the concept or early engineering phase of a project. However, for specific equipment like mobile plant, this could feasibly be done as late as the operation phase of a project, as the existing mobile plant reaches its end of life. Reducing the speed or power of the source. Slowing things down is a good general principle for reducing noise. The selection of lower speed equipment is best done during the early engineering or detailed design phase when enough detail is known about the required equipment duty that appropriate procurement specifications can be produced and issued to bidders for tendering. An example would be, instead of using a 2-pole fixed speed electric motor that runs at 3000 RPM, use a 4-pole motor that runs at half the speed. or a 6 or 8 pole motor that runs at 1/3 or 1/4 of the speed. This could result in a significant reduction in noise from the motor. The example of slowing down cooling fans demonstrates why slowing things down can be so effective at reducing noise. The noise from the fan, or the sound power level, is related to the fifth power of the tip speed of the blades. Reducing the speed has a dramatic effect on the noise reduction. For example, halving the speed of the fan gives you a 15 dB reduction in noise generated by the fan. This type of change would have the most positive impact during the early engineering phase of a project and could have implications such as the selection of variable speed electric motors instead of fixed speed electric motors for the fans. Here is an example of reducing aerodynamic drag by using aerodynamically profiled low noise fan blades. The first fan you see is a standard fan blade design using straight pressed metal fan blades. These blades generate a lot of drag and are inefficient. The second fan uses a fan blade design with a swept blade geometry. These blades create less drag, and so they lose less energy as noise. Reductions of up to 20 dB are possible by switching to aerodynamic profiled fan blades. There's another way to reduce aerodynamic drag on fans, and that is to use a diffuser to smooth out the discharge air as it leaves the fan cooler. Without a diffuser, the air leaving the fan has large velocity gradients that create turbulence and noise. With a diffuser attached to the discharge of the cooling fan, the velocity gradients are smoother, which mean reduced turbulence and hence reduced noise. Diffusers can reduce noise by up to 7 dB. Apart from reduced noise, the increased efficiency can translate into potentially a 27% reduction in energy consumption for a given volume of air. Once we've exhausted all the previous options and we find that we still need to reduce the noise, then we have to look at path treatment options. That means that we are looking at ways to interrupt the path of the noise from the source to the receiver. Often, the most effective path treatment is an acoustic enclosure. This is essentially a box around the equipment that contains the noise. The inside surfaces are normally treated with acoustic absorption to absorb as much noise as possible before it finds its way out of the enclosure, mostly through openings or gaps, but some through the walls. The openings are acoustic weak points, and additional acoustic treatments are required at these points. The principle of the treatment of the enclosure walls is as follows. The noise inside the enclosure encounters the inner surface of the cladding, which is comprised of perforated sheet metal. The perforations allow the noise to enter the absorptive material that is packed between the inner and outer layer of the cladding. Most of the noise is absorbed by the mineral wool by conversion into heat. The remaining noise that is not converted into heat is transmitted through the outer layer of the cladding. Enclosures can provide up to 40 dB reduction. Because enclosures take up additional space and may require additional systems like fire and gas detection and ventilation, they should be considered during early engineering design. The silencer is a commonly used path treatment option for noisy piping. It works on a similar principle as the acoustic enclosure. Noise enters the silencer and encounters perforated steel tubes that allow the noise to enter the absorptive material. Most of the noise is absorbed by the mineral wool, Some of the noise will be transmitted through the silencer body to the outside. The rest will be transmitted to the downstream piping. Silencers can provide up to 45 dB of attenuation. It is best to specify silencers during the early engineering phase of a project, relying on experience and judgment about where it is needed, since vendor data may not be available for the upstream noise source. This ensures that the piping design makes allowance for the silencer in terms of layout and static load. During detailed engineering, the requirement for the silencer can be confirmed once vendor data is available. Where it is found to be unnecessary, the silencer can be removed from the design with minimal change to the piping design. It is far more difficult to add a silencer into a mature piping design than to remove one that isn't needed. Acoustic enclosures and silencers are two of the most common and most effective path treatment options, but they are often the most expensive and should be considered as early as possible in the design. There are other simpler and cheaper path treatment options that may be suitable when the required noise reductions are not so demanding, such as acoustic blankets or noise barriers. But these normally don't require early consideration during design, since their impact to the project is not normally significant. Before we close, let's take a moment to reflect on what we've covered today. Industrial noise isn't just a compliance obligation. It affects worker safety, community well-being, and the long-term health of the people who work in and near industrial facilities. We've seen how noise impacts not only hearing, but stress, cognition, communication, and overall quality of life. We explored how noise is generated, how it propagates, and how we use modelling tools to predict and visualize its impact. And most importantly, we discussed practical, effective engineering solutions that reduce our reliance on hearing protection, from eliminating noise sources to substituting quieter technologies, improving efficiency, reducing speed and power, and applying targeted path treatment controls. The key message is clear. The most effective noise control happens at the design stage. By identifying significant noise sources early and applying sound engineering principles, we can avoid overengineering, reduce project risk, and design quieter, safer, and more sustainable facilities. Thank you for spending your time with us today and for your interest in finding out how we help our clients to achieve safer workplaces and stronger communities. If you have any further questions or would like support on applying noise control design principles in your projects, please reach out. We're here to help.
Okay, thank you very much, Wayne and Domian. We're now going to take a moment and address some of the questions that we've received from the audience. And again, to our audience members, please make use of the Q&A tab to ask any questions. So Wayne, I have the first question here, and I'm going to ask you to address this one. And it reads like this. What are the typical and mostly problematic noise sources for industrial facilities that you typically design? And how do you mitigate them?
The typical noise sources we would find for industrial facilities depends on what type of facility there is. So if it's, say, for example, an oil and gas processing facility or something like an LNG facility, when we're looking at the environmental impact, it's actually things like air coolers, because there are so many air coolers on an LNG plant, sometimes in the hundreds or even thousands, and they radiate low frequency noise, and that can propagate quite far without much absorption in the atmosphere. The other noise source that can be a problem on large industrial plant could be power generation sources such as gas turbine generators. The gas turbine itself is noisy, but usually that's not a problem because that can be contained by acoustic enclosures. It's the exhaust that can be problematic because, again, the combustion noise is low frequency and the stacks are elevated, and they can propagate quite far in terms of impacts to the communities. Other types of facilities, like mining facilities, the dominant source, which is quite difficult to control, is mobile equipment. It's haul trucks, it's diggers, graders, that sort of thing. In an active mine site, it's that mobile equipment, and the processing equipment from mine sites can also be quite loud, such as the shakers and the crushers. So with shakers and crushers, you can put the best option would be to put barriers in place. With gas turbines, with the exhaust from gas turbines, it's to ensure that in the design phase you specify an appropriate limit for the exhaust so that the gas turbine vendor is able to design a high temperature silencer to control that. So it needs to be considered during that phase rather than when it starts and operates, because after it starts up, adding noise controls to something like a gas turbine exhaust becomes very, very difficult because you're imposing additional constraints on a design that's been completed. And for air coolers, we've discussed it today, and that's why I focused on so many examples of how we can reduce noise from fans and air coolers, is because there are many options available, and most of them can only be feasibly implemented if we are considering it during the design phase. It's not practical to design and build acoustic enclosures around existing air coolers if you find that it's noisy when it starts up, because you need airflow for those air coolers, and acoustic enclosures don't really help with that.
Okay, great. Thank you very much, Wayne. We appreciate that. A couple of more questions here. The next question is in regard to uncertainties. So what are the main areas of uncertainties when you are modeling noise, and how do you handle them in your predictions? So Wayne, if you could share some thoughts on that, we'd appreciate it.
Yeah, the main area is really getting reliable source noise levels, how much noise each noise source is radiating. So the ideal situation is that we get measurements from the actual equipment itself, but the timing is not practical because we need to consider these issues during the design phase, so we won't have any equipment to measure. So we fall back to either taking measurements or relying on measurements from similar equipment in the past, or from previous noise levels that the vendor has provided on other projects. Or if we don't have that, then rely on generic prediction methods that have been developed based on sampling of equipment of similar types before. So that's the main area of uncertainty. There is uncertainty in terms of the propagation of noise. Where does the noise go after you've put it into the model? And because the weather conditions aren't as neat and clean as I presented in the presentation today, you get temperature gradients and wind speed gradients, but they vary from place to place, and they're changing all the time in terms of over time, over the season, over a particular time of the day, whether it's night or day, or whether it's summer or winter. And so the way that we have to handle the uncertainty of propagation is we have to assume a worst case scenario. And that's what the environmental regulators all expect, and that's what they write into their regulations when they're talking about considering environmental impacts. So the worst case conditions are during the nighttime, so early hours in the morning, when you get that temperature inversion, where you get a higher temperature at a higher elevation, and when you have wind speed gradients in the direction of the receiver. So that's the two main areas, which is getting the source noise. So we have to rely on measurements from past equipment if we can, and the environmental propagation. So we rely on having worst case scenarios.
Okay, great. Thank you very much, Wayne. I see we're getting a bit close to the top of the hour, but I think we can squeeze one more question in here. I know you spoke about some of the challenges throughout your presentation, but maybe I could ask this question. What are the biggest challenges that you have seen? And specifically, when you have a project that's looking like it could exceed its noise limits. So maybe just one other example with one or two perhaps examples, Wayne, with the time remaining.
The biggest challenge is actually getting the noise controls over the line. So when we have a facility that looks like it's going to be noisy, and we have a certain amount of noise control that will be required, the question that often comes back from the project is it absolutely necessary? How sure are you? How certain are you? And we can't say that we are absolutely certain because we're not measuring the actual built equipment. What we say is we have a certain level of uncertainty, but when you take into account that uncertainty, we still think that it's going to exceed it because we're relying on data that is expected rather than as measured. And one example is when we had significant exceed as predicted by some cooling towers that are on an LNG plant, and it was combined with the noise from the air coolers as well. So what we needed to do was we needed to slow down the air coolers, and for that we had to change the air coolers to variable speed drives so that we had, when there is a lower cooling duty required, we had all the fans run at a lower speed, instead of switching 30% of the fans off and leaving 70% of the fans running at full speed. So that's how we reduce the noise during a turn down when there's less cooling required. And then the cooling towers, they make splashing noise, so we can reduce noise by putting splash pads on at the bottom. And they also make a lot of low frequency noise from the fan itself. So it's changing to a more efficient swept blade, aerodynamic blade, as well as putting a longer diffuser on the end of the fan to smooth out the flow and reduce the noise levels there. So you can see the common theme there with the challenges we faced is the ones that are hardest to tackle are the ones such as air coolers and fans.
Okay, great. Well, thank you very much, Wayne. We appreciate that added context. It looks like that's all the time we have for questions now. I do see a few more questions coming in, but for those requesters, rest assured we'll get written responses back to you. And again, thanks, Wayne, for a very informative webinar and the time that you've spent both today with us and in preparation for today's event. And thank you to our audience for attending today. It certainly has been a pleasure being your moderator. Please continue to stay informed of these events by visiting the Innovation Builders page on Fluor.com or following our social media channels using hashtag InnovationBuilders. If you'd like us to send you email notifications of future webinars, please email us at innovation.builders@fluor.com with opt-in in the subject line. We appreciate your attention and thank you again for dialing in today. We will send out a compiled list of the Q&A shortly, along with the notification that the webinar recording is available for replay on Fluor.com. If you have any questions or require additional information, please email innovation.builders@fluor.com and someone from our team will get back to you. And finally, from all of us at the Innovation Builders team, have a safe day and thank you.